Alright, so in this video we go over section 6.3, the fundamental theorem of calculus and the definite integral. Alright, so as opposed to the integrals that we evaluated in the previous sections, we just did what we call indefinite integrals. In this case, we are going to evaluate an integral within an interval AB. But what does that represent? So when we evaluate an integral like this, all we're doing is basically consider this function f of x, the graph of f of x, and evaluate it from a to b. All we are doing is finding the area under the curve. That's the meaning of evaluating a definite integral. And the integration rules that we have been using in the previous videos, they're going to work exactly the same way, just like the general power rule, the ln rule, the exponential rule, etc. However, all we do is evaluate the integral at the upper limit and subtract what we obtain from evaluating at the lower limit. So let's do a couple of examples. Let's do a very simple example in which we evaluate these integrals. Okay, so let's see. So the integral of 2x, it's going to be, well, 2x is the derivative of x squared. But in this case, we don't put the plus c anymore. We put this little bar and we say that we evaluate it from 1 to 2. So quantity squared minus quantity squared. Alright, so in this case, it's going to be 2 squared minus 1 squared. In this case, this represents the f of b. This is our b, if you will. And this represents the f of a, which is right here. B is the upper limit, a is the lower limit. All we do is just compute this operation. 2 squared, which is 4, minus 1 squared, which is 1. The value of the integral is 3. So this represents, so that's 1, 2, 3, 1, 2, 3. Ultimately, I mean, I'm not going to ask to do this on the homework, and I'm not going to do this every single problem. Just for this example, we have the graph of f of x equals 2x, which looks kind of like this. It's a straight line with a slope of 2 and a y-intercept at 0. And it gets evaluated from 1 to 2. So all we're doing here is finding the area from 1 to 2. This area right here, which is 3 units. Okay, so that's the interpretation, the geometric interpretation. So let's do another example that combines a few rules at the same time. So in this case, we have the integral of x squared. So the integral of x squared is x cubed over 3. The integral of 1 over x is ln of absolute value of x, and minus 3 times the integral of e to the x, which is itself e to the x. Notice in this case, x is not being multiplied by any constant, so we had to divide anything, so not in this case. So we evaluate this from 1 to 2, and we do the upper limit first, the evaluation of the upper limit, and then the evaluation of the lower limit. So we write this as something cubed over 3 plus ln of blank minus 3 times e to the blank. Okay. So in this case, I'm going to evaluate the 2, the upper limit. Alright, in this case, this represents b, minus something cubed rather over 3 plus ln of blank for now minus 3 e to the blank. Alright, so this is going to be 1 ln of 1 e to the 1. Alright, well, you might want to start simplifying a few things. For example, this quantity ln of 1 goes to 0. And here you might want to just denote that this is f of a. F evaluated at a lower limit, which in this case is this one right here. Okay? So let's simplify this. In this case, we are going to cube the 2, so we get 8 thirds ln up 2. That's simply ln up 2. No more absolute value bars because that's simply a number. That's just a constant. Minus 3e squared. Okay. And then minus, be careful here, that's going to be 1/3. And plus 0, I don't need to write that one, minus 3e to the first, simply e. So here you might want to distribute the negative to both of these two terms. Okay, so that's going to give us 8 thirds plus ln up 2 minus 3e squared minus 1/3 plus 3e. So in this case, notice how we have a couple of like terms. That is the 8 thirds and the 1/3. So we can simplify those to 7 thirds plus ln up 2 minus 3e squared plus 3e. And you can leave it like this. Alternatively, you might want to use a graphing calculator and get decimals, so it's going to depend on the purpose. So in the meantime, I'm okay with this. The homework, however, will ask you to use the graphing calculator and provide maybe 2 or 3 decimal places. Let's go over a couple more examples. So now let's do some using substitution. So when it comes to use substitution, we need to do a little bit more than just do the integration. We need to also change the limits. How does that work? Well, I'll show you in these few examples. So in this case, notice the quantity inside of the radical is 1 degree higher than the one outside. So might as well, that's going to work as our u. So the differential du equals 2x dx. So I'm going to rewrite this integral slightly, okay? From 0 to 1, square root of x squared plus 1 times x dx. And notice the little space I left here for those correction factors. Now observe something here. Just like we did on the previous video, we were comparing the x dx with what we got here. So there we wish we had the 2 there. We can put it there. Notice it's outside of the radical sign, not inside. And provided you divide 1 out. Okay, so in this case, this is going to be our du. Alright, this is our du. Now what's next? Well, so the next step is to do the substitution. So 1/2 times the integral of square root of u du. But what about the limits? So what are we doing when we do substitution? So when we do substitution, we are given a complicated looking integral in which we move this integral, we convert this integral from the world of x to the world of u, which is simpler. We evaluate this or solve the problem in the easier world, and then we go back substitute to get the result in terms of the variable that we started initially. Now the thing is, in this case, we are changing all expressions that have x into expressions that have u. But the thing is, we have to also change the limits and express them in terms of the world of u, because not only the expressions get carried to the world of u, but also the limits of integration. How are we going to go and do that? Well, we're going to use our expression of u. We are going to evaluate u at a lower limit, which is 0. That's going to be 0 squared plus 1, which is going to give us 1, and u evaluated at the upper limit, which is 1. And that's going to be 1 squared plus 1, which will give us 1 squared plus 1 squared is 1 plus 1, that's a 2. So the new limits of integration, 0 becomes 1, so, and 1 becomes 2. Okay. Why do we do this? Because that's going to help us avoid tedious calculations when we do the back substitution. In fact, doing this will keep us from doing the back substitution and will help us save a lot of time. Okay, so let's do the integration of this. I cannot integrate the radical just right away, so I'm going to change it to terms of rational exponents. So the integral of u to the 1/2 will be 1/2 u to the 1/2 plus 1. That's going to give us 3/2 over 3/2, evaluated from 1 to 2. So no need to back substitute like we did before, because if we do back substitute, then we will have to use the older limits. So that's why we come up with new limits to simplify calculations. So here, let me simplify this before substituting any numbers. Number 1, I'm going to write these 3/2 as 2/3 times 1/2. And then I'm going to go back to write this 3/2 into radical form, because we are going to compute numerical calculations. So we need to write those in radical form. So just to recall, when we have, let me say, a to the m over n, this is the nth root of a to the m, or the nth root of a, the whole quantity to the m. I'm going to use this one. Okay, so this is a fact from algebra, from elementary and intermediate algebra. So I'm going to write this as the square root of u quantity cubed, evaluated from 1 to 2. Okay, so it would be worth to put a box for this. Okay, so I'm going to continue here. I'm going to go from here to over here. So this is going to be, oh, by the way, notice how these 2's cancel, they go away, and I will be left with 1/3. So I'm going to have 1/3. First of all, the upper limit, which is the square root of two quantity cubed minus the square root of 1 quantity cubed. Okay, how can we simplify this? Is there a way? Because this, I'm worried about this square root 2 quantity cubed. Yes, there's a way to simplify this. So number 1, the square root of 1 is simply 1, and then 1 cubed is going to give us 1. I'm going to go back and write this inside. So this is going to be 1/3 times square root of, this will be 2 cubed minus 1. Again, from intermediate algebra, you know you can simplify this by 2 squared times 2 minus 1. And this guy can be taken they can be taken outside of the radical. So this will be 1/3 times 2 square root of 2 minus 1. Final answer for this. Okay, and again, unless you are required to report on your final answer on the homework using decimals, just put this in the calculator. Alright, let's do another example. So for letter D, Let's see. Observe the exponent of the exponential function. It's x squared minus 1, which is 1 degree higher than the quantity quantity in front of it. So let me rewrite this. 1 to 3, and this is e to the x squared minus 1. I'm going to leave some space here, x dx, because most likely we are going to use a correction factor. So number one, let's set up the u du. U equals x squared minus 1, du equals 2x dx. That's our differential. So we need a correction factor. We need a 2 here, provided we can put it there, provided we divided 1 out. Okay, so notice how this works perfectly for our du. Alright, so let's rewrite the integral in terms of u. So we are going to have 1/2 integral from 1 to 3 of e to the u du. By the way, I shouldn't have written that those limits of integration. Let me correct that, because we need to change those in the new world. Again, I'm glad I made this mistake here, because that's a very common mistake, to keep carrying the older limits, and you don't want to do that when doing the homework or in exams. Okay, it would be frustrating to do the work keeping the old limits, giving you a wrong answer. So let's figure out what the new limits of integration are. So u evaluated at the lower limit, which is 1, it's going to give us 1 squared plus 1, minus 1 rather, which is going to give us a 0. So the lower limit now is 0. And let's evaluate let's find out what the upper limit is, what the new upper limit is, by plugging the number 3, this u, 3 squared minus 1, so that's 9 minus 1, which is 8th. So now we integrate e to the u, and that's a very simple integral. E to the u, that's 1/2. The integral of e to the u is simply e to the u evaluated from 0 to 8th. So let's do upper limit. So right now let me factor out that 1/2. So it's going to be e to the 8th minus e to the 0. E to the 8th, just leave it like that. However, e to the 0, you might want to express that as simply 1, because that any quantity to the 0 power is 1. So we're going to have as a final answer 1/2 of e to the 8th minus 1. Okay. Let's do one last example. So in this case, well, this integral might look a little bit tricky. ln, and next in the denominator. Well, let's see. So in this case, we don't see the pattern higher degree than and lower degree as in the other examples. However, we can, if we rewrite this integral, 1 to 3, 1 plus ln of x times 1 over x dx. Okay. In this case, the quantity inside of the parentheses, if we take the derivative of 1 is 0, the derivative of ln of x is 1 over x. So that's how, or that's why rather, u will work as 1 plus ln of x. So du will be derivative of 1 is 0, derivative of ln of x will be 1 over x dx. Okay, so we are going to rewrite the integral. Don't write anything for the limits yet, because we still need to change them. So this is u du, and in this case we don't need any correction factors, because notice how 1 over x dx, 1 over x dx, they are both there. See? So now let's change the limits into the new world. So u evaluated at 1 and u evaluated at 3. Okay, so we are going to have 1 plus ln of 1. ln of 1 is 0, that's going to give us just 1. And this is going to be 1 plus ln of 3. In this case, is simply ln of 3. Keep it as it is. Okay, so this is going to go from 1 to 1 plus ln of 3. Yes, it's a weird looking limit of integration, but yes, we are keeping the original form. All right, we're keeping the original form. The exact form rather. So the integral of u du, what is that? Well, u squared over 2 evaluated from 1 to 1 plus ln of 3. Okay, so now the next step is to evaluate the function at the upper limit and then the lower limit. So 1 half, I'm going to have 1 plus ln of 3 squared minus 1 squared, which is going to be simply 1. So you might want to just clear that one, and no need to bother expanding this binomial here. That's fine. That works. That's good enough for final answer. So this is going to be 1 plus ln of 3 and quantity squared minus 1. Final answer. Exact answer. That's enough. Okay, so this is it for this video. See you on the next topic.